Okay, the definite integral then. That's what we're going to look at, the definite integral. And it's a way of finding the area under a function. So here's a function being drawn, this function fx, and it looks like this, the curve. And we're interested in what's the area under this curve between the limits a and b. So we call these limits a and b. And the notation is this. So if I want to find the area underneath the curve, it is equal to the integral between the limits a and b of the function with respect to x. So that's how we'd write it. What's the area underneath here? It's the area, it's the integral between these limits. So as soon as you see numbers here, you know you're finding a definite integral, and you're after the area underneath the curve between those points. Last week we were looking at the integral of the function, which is a new type of function, no limits on it. So in that case we're just finding a function that might tell us the area if we wanted to put limits in. We have to be a bit careful sometimes about functions when we're looking at them, because if, say, I looked at the sine function, which is drawn here, then if I found the area between the limits a and b on here, and we might think about what those limits are if it was just sine x, then we're going to end up with a total area of 0, because those two areas will cancel each other out. So sometimes we have to think about the limits that we're using and make sure that we're not going to end up with results that aren't useful to us. So let's have a look at an example of a definite integral. There it is. I'd say find the integral of that function x squared between the limits 1 and 3. And I'm going to go through the exact method to how we do this with the sort of notation and that we do use to do it. Okay, so first job is to integrate it. Add 1 to the power, divide by the new power. So x squared becomes x cubed divided by 3 plus c. Sorry, first thing I do is integrate it and I get this. So I don't need the integral symbol anymore, do I? So I integrate it and I get this. That's the answer. And now I've got to put the limits in. So to signify this, I put square brackets around it and put the limits in 1 and 3. We will find when we finish this problem that c disappears. So actually, for further problems, if you're doing a definite integral, you don't include the c, but I'm going to include it in this particular example so I can demonstrate why we ignore it. So there's our integral. Don't know what c is. So what we do now is we just put in our limits. We let x equal the top limit first, work out what the answer is, and then we let x equal the bottom limit, which is 1, work out what that is, and then take 1 away from the other. So again, the sort of notation we'll use, it's common to use curly brackets like this to demonstrate that I'm now putting the numbers in. So top limit, 3, x is 3, cubed over 3 plus c. Minus, put the bottom limit in, x is 1, 1 cubed over 3 plus c. If it's a complex integral that you're trying to do, in this case, it's a good idea to just rewrite the function. I've just rewritten the function here, and instead of x, I've put the value in a bracket. That's a good idea, and that leads to less errors. So now we can calculate what they are. 3 cubed, well actually, in this particular case, I've got 3 cancelling out one of the 3's here, so it ends up being 3 squared, which is just 9. Plus c minus 1 cubed is 1 divided by 3, so that's a third plus c. Note I'm subtracting this bracket from this bracket. So at this point c minus c is gone. And that will always happen. When I do a definite integral, I subtract the bottom limit from the top limit, so that c disappears. So in practice, whenever we do a definite integral, we don't include it, because that is always the case. So if I plot this function, and you've got the plot at the bottom of your notes there, what we've done effectively is found this area between 1 and 3. We found that area. And it turns out to be 9 minus a third, which is 8 2/3. So I know that this area is 8 2/3, or 8.67 if we wanted to write it as a decimal. Now that area might represent something. If I'd plotted up here velocity and along here time, so in other words, we had velocity here measured in meters per second and time measured in seconds, that area would represent something about that motion. What would it represent? Called this. So it represents the displacement. Say it was going at a constant speed of 6 meters per second for 3 seconds. 6 meters per second for 3 seconds, you've gone 18 meters, and that's the area underneath that rectangle. 6 times 3 is 18. So the area represents the displacement if we were plotting velocity against time. If we were plotting force, so this was the experiment we did in the science engineering thing, and we're extending something, so this was force in newtons against extension in meters, say, what would that area underneath that curve represent then? What do I get if I multiply force by distance? Force times distance, that's a formula we've used, equals, sorry? No, not, yes, it is the moment. If you're talking about something moving, yes, that's true. So the moment of the force, or, I'm thinking more generally now, it's the work done. Force times distance is the work done. So in this case, the area would be the work done, measured in joules, or the moment. So it's useful to find the area underneath the function because it often represents something we're interested in finding out, either the work done or the displacement of something.